So heading into our final presentation of the day, again, as we've had with some other presenters here, this gentleman will come as no stranger to the Water Online community, to the Virtual Water Expo audience. I do apologize in advance. We don't have video or visual of this young man, so I know we'll probably get some notes demanding that the audience be able to see this industry expert and mystery guest. But without further ado, I'm going to unveil the mask here. Although we can't see him, we can hear him, and he will be able to give us a fantastic presentation, as he always does. Ladies and gentlemen, bringing to you why the wrong blower technology will cost you more money is none other than Tom McCurdy. Tom, take us away.
Wow, that was quite an intro, Travis. I really appreciate that.
You definitely deserve it. I'm looking forward to this.
All right. Well, I hope I don't disappoint here. So, all right, let's move on here. Hopefully my video is working as well, or my the slides are working. Let me see here. Okay.
You are indeed up next. So
I know.
We do see that. We do see that.
I'm trying to advance the slides here. I'm having a little trouble. So there we go.
That's okay.
All right, good.
Now we're rolling now. Yes, awesome. We are rolling now.
All right, excellent. Okay, so the big thing about blowers is that they're big energy consumers in a wastewater treatment plant. Probably 50 to 60% of the electric bill. And depending on the community, it could be as much as 4% of the total municipality's power usage. So energy efficiency becomes kind of a big deal. And so in a wastewater treatment plant, it's probably on the top three. The blower power being maybe one of the top ones, sludge disposal and personnel costs. So energy efficiency becomes kind of a big deal. And picking the correct technology becomes a big deal as well. So big questions here would be, how much do they consume? What are the available technologies? Does sizing of the technology or the blowers themselves matter? And how can the plant realize the savings beyond what's actually on the performance curve? So I'm going to focus on the products that Aerzen brings to the table: the screw type, the single gear, single stage gear turbo, and the high speed turbo blower for my presentation today. The screw type blower has become probably one of the fastest growing technologies in a wastewater treatment plant. And because primarily it has, depending on the pressure, energy efficiency that's comparable to these single stage centrifugals. So why would you use one over the other? Well, it's this table kind of shows what some of the comparative features here. Single stage centrifugal is definitely high efficiency at all pressures. The low pressure screw, because it's actually compressing the air inside the blower stage itself, it's the closer you get to the sort of the sweet spot or the sweet zone of efficiency, the more efficient it's going to be. The screw blower is built to a specific compression ratio itself, and typically when you get above 8 psi, you're getting into the area where you're really starting to see the energy efficiency. Turn down is another area that's probably more prevalent, where they've just replaced new blowers or older blowers with newer blowers, because they're sizing the blowers for some level of expansion in the future. Where you run right now becomes very important, and this becomes a major factor in the turn down ability, meaning the ability of a blower to reduce its flow from the design point to the minimum. And you can see screw compressors can be much more flexible than a single stage centrifugal. Cost is comparable to turbo. It's as you get into the bigger sizes, you're buying a lot more metal with a screw compressor because it's positive displacement, and so you have those bigger lobes, you have a bigger footprint. So the single stage centrifugals can be a little bit more cost effective when you start to get up above 200 horsepower. Footprint is comparable. Control is linear, which can be a very big factor when you're dealing with standard VFDs. And then the electricity, typically, again, a standard VFD, high-speed turbo, you really don't have the flexibility to go with a medium voltage, whereas with an integral gear turbo, you do. So proper selection into the right technology, meaning the technology that it's feeding into. An activated sludge basin with conventional aeration, typically a fixed pressure, so you have a constant level and a variable flow. Actually, any of the technologies would be appropriate. On an SBR, where you typically have varying pressure, especially when you're doing a mixed fill, you're really more in the realm of positive displacement, because positive displacement is constant volume against the varying pressure, meaning no matter what the level is, as long as you have enough motor horsepower to overcome that higher level, you're good. Whereas with the turbo, it basically lives on the performance curve based on the size and the configuration of the impeller itself. So you may run into trouble here, or you might not. MBR, typically it's open to any of the blower technologies. And MBBR, which you probably see more in high-strength waste than maybe in industrial wastewater treatment plants. It's more the realm of the higher pressure technologies. So what gave rise to these more efficient technologies? It really was all about the money. I mean, in the mid-2000s, or the mid-aughts, there were a lot of utilities out there that were providing grant money to utilities, to municipal plants, to offset the cost of the higher cost of a more efficient technology. And so this gave rise to a lot of the, especially the high-speed turbos that you see on the market today. So the major manufacturers today, what you'll see on the low-pressure screw is that the typically major manufacturers would be Aerzen, Atlas Copco, and Kaiser. You saw the presentation from my colleague at Kaiser before. The high-speed turbo, you typically see Aerzen, Noros, and ABS. And ABS actually is now called Sulzer. And then on the gear turbo, there was Lone Star, Next Turbo, and Turblex, which is now owned by Howden. So what was the key to success with any of these technologies? Probably the biggest key was reliability. You know, when the high-speed turbos first came out onto the market, there was still a bit of a learning curve that accompanied that, because they were still sort of learning the market and they kind of overexpanded. But the companies that were sticking around were the ones that invested in the technology itself and made it more robust in the wastewater treatment market. The low pressure screw was actually built on established screw compressor technology. The high speed turbo, again, improved the thermal robustness, the tolerance of the power swings, and the bearing surface material itself. And then the gear turbo was actually built on the old Turblex technology. And now that it had more competition, that market got softened a bit. So how do you compare the technologies that are available for a given application? Well, because Aerzen has all three of the major technologies, meaning the the turbo, the screw compressor, which we call our hybrid, as well as our PD blower, we can actually run a comparison on site based on the site conditions. And you could see for this particular example, this example being pressure of 8 psig and approximately a top end of 2500 SCFM. Big performance advantage versus a standard PD. And that applies to either the screw compressor or the high-speed turbo. And when it came down to the turn down level, which I mentioned in the previous, one of the previous slides, you actually get much better turn down with the screw compressor than you do with the high-speed turbo. And again, what we're doing here is I'm comparing all of the Aerzen technologies. I'm not looking at any competitors here. And again, comparable performance. So what does that mean in the system? Well, you're not only dealing with efficiency, but you're also dealing with capital cost and as well as the turn down. And just looking at a snapshot of the three technologies that we had available for this particular project, it looked like the turbo was certainly the cheapest of the three in terms of capital cost. It was equivalent to the screw compressor, again, in this example, but the big advantage that the screw compressor had was the amount of minimum flow that was available. So depending on the operating conditions that that particular plant was running, it could either go with the turbo if this low point was okay on the as far as operating goes, or if it needed to be much lower, then this may be the way to go. So when a company or when a utility is doing an energy evaluation, what I did previously was just a design point comparison. It really matters to do a decent evaluation, based on what you're expecting in terms of the operating conditions. At the very least, do the hot day maximum, the cold day minimum, and at least the seasonal average to determine what your anticipated power usage is going to be over the course of the year. And again, a little bit of a crystal ball here, especially if it's new equipment, but at least this gives you a comparison to look at all of the companies that are competing on a particular project. And the way you do that, you look at the anticipated operating points, assign time and conditions, and require the manufacturer to provide the total amount of power that's required. Now, I say this primarily because of the high-speed turbo. When the high-speed turbo first came out into the market, it was a much more integrated package because you had the VFD or inverter inside the package. You have the control panel, you had cooling inside that package. It was not a clear-cut, take the stage efficiency and then compare it to the others. So this is why PTC 13 came along, which was not only a way to verify the performance for high-speed turbo, but also for the other technologies as well. And Aerzen actually built a PTC 13 performance or test bay, which was good up to 1,000 horsepower. So, so we are able to at least give you an even playing field from our standpoint. The other aspect of sizing is, typically when an engineer is designing a project, their big bite at the apple is this capital improvement project. And what they have to come into, what they have to factor is the potential expansion, whether it's additional housing projects that are going up, additional industrial users that might be moving into a community. But typically what I see is when it goes from the 90% design to 100% design, they'll add a little bit of a cushion. And the problem with that is no matter what the supplier is, that could throw them into the next size up. And the problem is come bid day, when we've been working on a specific size of a blower, all of a sudden they're adding additional flow or doing unrealistic ambient conditions that end up throwing us into a larger size machine, or throwing any manufacturer into a larger size machine, and costing the project more, and also forsaking the minimum flows. Here's an example here. What may end up happening is, if you end up bumping up the flows, like say from 3,000 CFM to 3,500 CFM, this was the model that we would have had available for the screw compressor. If you bump it up to 3,500 SCFM, all of a sudden we're in the next size. All of a sudden the cost goes up by a major factor, the pipe size goes up by a major factor, and then suddenly the footprint is no longer what they had originally sized it around, but now we're in a bigger unit. And this is more common than you think. So it's something to watch out for when you are working with your consultant as an owner at the plant. So another factor is ambient conditions. Again, a big impact on the sizing of the unit itself. Here's an example in a California plant where we had 2 large turbos and 2 small turbos, and what the idea was that the smaller turbo was going to act as a jockey blower, and when the maximum value was hit from the jockey blower and the demand was still higher, the larger blowers would turn on. So the idea here is to make sure that the maximum for the smaller blower effectively overlaps beyond the minimum of the larger blower. So that was all well and good until they assigned 115 degrees Fahrenheit maximum temperature and 90% relative humidity. And the problem was it limited the top end flow, and it all of a sudden brought it out of the realm of reality and more into the next size. And what I mean by out of the realm of reality was, if you looked at, this is one of those heat and humidity indexes, and for 115 degrees, it's not even on the curve. You combine that with relative humidity of 95%, this is actually unlivable conditions. So it's not something you're ever going to run into, but there it was in the specification, and we had to meet it. So the caution here is to make sure that at least the ambient conditions and the maximum flows are somewhat closer to the reality of what the plant is going to face. Now, one thing that some engineers have done is to actually add a bypass on the compressed air line. Now, you think about it. We went through a lot of exercise in trying to figure out the most efficient machine possible for the particular application. And here, the engineer comes in and says, well, if we need it, we're going to bypass this. We're going to blow this efficient air into the atmosphere. And usually this is when the conditions are such that the flows are low and the BODs are low, and it's in the middle of the night. So we're waking up the neighbors and wasting money. So again, another caution where you're just taking all that money and just blowing it away. So using a jockey blower is usually the better way of addressing these low flows, rather than worrying about the minimums on the main process blowers. If you can have a smaller blower that can actually take up those minimums and not bypass, you're well ahead of the game. So the takeaways here would be to determine the proper technology for a given application. Consider the integrity of the manufacturer, especially if you're using a newer technology. Reliability is absolutely key with this. so that you know that you're dealing with a manufacturer that has a reliable product with a proven track record. Consider your current flow requirements when deciding on the blower size, especially the low flows, and evaluate your energy use properly. So I'll leave you with this. Which technology is best? If all you have is a hammer, everything looks like a nail. So with that, I will take any questions that you have available.
Well put, Tom. Well put. As always, great presentation. I have about 30 seconds here, and I have a question. So if you could go lightning round on me here.
Here we go.
So after the first sizing warning slide, why wouldn't the municipality want the biggest machines they can get? I mean, especially if there's a chance at funding the project.
Absolutely. You know, and that is a very common question. It's like, this is our bite at the apple. This is our time to get the to get this capital funding. So I want to get the most that I can. And the problem is it ends up being oversized, so that what you're dealing with in the current condition may not be able to be reached by the minimum available flow from the blowers that you're dealing with.
Makes sense. That was very efficient in terms of the time there with that question, so I appreciate it. Good job as always, Tom. I can't wait to have you back for next time. But fantastic. Thank you for joining us here.
Looking forward to it.
Much appreciated, Tom.
All right. Thank you.